Okay, so far we got the angular acceleration, and also the average angular velocity for the first 10 seconds. Okay, next we're finding the angular velocity at 5 seconds. So this is an instantaneous velocity, and similar to the equation that we got here, omega is alpha times t, and we can use that, but t is 5, not 10 in this case, so we need to be careful with that. And alpha we already found out here, so put those together and you're gonna get 4 radians per second. That's what I was trying to say, like, because 5 seconds is in between, in the middle of 10 seconds, the value is gonna be the same as the average, okay, because it starts from 0 as well. So that's why I estimated that these two should be the same, and I'm gonna box this answer as well. So this is for part C. And now for the last part, let's just check again the additional angle the disk rotates through during the following 10 seconds. So I cannot use the same step-by-step process. I have to start over. And what do I do then? Again, my first step, writing those two equations, right? And then think about what is at the start. So if you are not using the first 10 seconds and you're starting your the last 10 seconds from in the middle after the first 10 seconds, then you don't have initial omega to be 0. Instead, you have initial omega to be 8 radians per second. Where did that come from? It came from this equation here. I'm gonna use a different color. And again, this is omega, right? At 10 seconds, what is omega? You know that alpha is 8 seconds. Okay, I'm gonna make this smaller. And we have this to be 0.8 times 10, right? And radians per second squared times second. It gives you 8 radians per second, okay? So that's where it comes from. So we're gonna use these and find out the rest of the problem. Okay, get back my blue color. And so what else do we know at the start? In this case, theta 0 is also not 0, but it is 40 radians. So this is where we left after the first 10 seconds. At the end, time is 10 seconds because, again, we are resetting the time to 0 from the start. And angular acceleration is the same, it's not changing, so we're going to make use of what we found in part A. And third step is putting all these together, right, in the equation. So when you rewrite this equation here, the first one, this is what you get. Theta equals to 40 radians plus 8 radians per second times 10 seconds plus 1/2 0.8 radians per second squared times 10 seconds, the whole thing squared. And that gives you 160 radians, okay? But again, you didn't measure that from 0, and that means you need to find the change, you need to take off that initial 40 radians, so you have to do this algebra here, and 160 radians minus 40, it gives you 120 radians, and that's the difference from the first, like, 10 seconds to up to 20 seconds, if you would say it that way. So the total motion is like up to 20 seconds. Okay, so this is the last 10 seconds, how much that the position was changed. Or it's the angular displacement from the first 10 to the final, okay, to the last 10. And again, the answers seem feasible. These problems are very similar to the linear motion problems with constant acceleration. So we applied a similar strategy. We use a step-by-step process. Step 1 is, one more time, I'm going to repeat that. This is our step 1, writing the equations. Step 2 is writing what we know at the end, at the start and at the end. And this part is our step 3. Where we plug things in to the first equations, first step, and just solving for the unknowns. Okay. And I'm gonna conclude today's class here. After that, we will continue with the next of the chapter on Monday.